Hello and welcome to a digital lecture for Salt Lake Community College. This lecture will cover section 6.3 for Intro to Statistics, considering fitting a line by least squares regression. In the previous section, we covered residuals, which is the difference between an observed value and its predicted value from a linear model, oftentimes represented with a variable e. Our goal is to minimize these as much as possible, which leads us to the best linear model we can find. If you square and sum these residuals, we get the least squares criterion, the specific value we are trying to minimize. If we are able to do so, we then find the least squares regression line, the optimal line of best fit for linear models. Finding this, though, is not convenient to do by hand. So, you should instead be using technology to find the regression line. In a regression line, we will have a slope and a y-intercept, both of which we attempt to interpret in terms of the specific situation. The slope describes the estimated difference in the y variable if the explanatory variable x for an observational unit happened to be 1 unit larger. The y-intercept describes the average outcome of y if x equals 0 and the linear model is valid all the way to 0, which in many applications is not the case. Note, the slope should always be interpreted so long as the correlation coefficient confirms that we have a linear relationship. If we have a linear relationship, the y-intercept still may not make sense, such as when talking about an explanatory variable for the height of adults. A height of x equals 0 feet or meters is illogical. Overall, keep in mind that if we find a linear relationship, we only know that it is true for the observed range of the data. We have no idea what the trend of data looks like outside of our observational range. It is dangerous to what we call extrapolate outside the realm of the original data. Extrapolation meaning applying a model estimate to values outside of the realm of the original data. From R, the correlation coefficient, we also have what is known as just simply R squared, or sometimes the coefficient of determination, which is a more common way to explain the strength of a linear fit, which is the square of the correlation coefficient R. The coefficient of determination R squared has some other applications even outside of linear data. However, again, we only talk about linear relationships in this course. Let's look at an example with a scatter plot. Here, the scatter plot shows the relationship percent of children receiving reduced fee school lunches and the percent of people wearing helmets when biking in the neighborhood. The calculated regression equation is y hat equals 55.34 minus 0.537 times x, and the correlation coefficient is r equals negative 0.849. Note that correlation coefficient of negative 0.849 is rather good. It is very close to negative 1, implying that we do have a linear relationship, specifically a negative linear relationship. Therefore, we should be able to consider looking at the slope and the y-intercept in this situation. First, for the y-intercept. When we're interpreting the y-intercept, what we're going to begin with is how the x value changes. Specifically, we're going to say how x changes by 1 unit. So here we'll say when the children receiving reduced fee lunch, which is x, increases by 1%. The y variable, people wearing helmets when biking, decreases by 0.537% on average. Keep in mind that both of these values are in percentages. It also shows that on the scatter plot. So that 0.537 is itself already percent. This is how we interpret the slope. As x increases by 1, the y variable will increase or decrease by whatever the value of the slope is. Also note that I did not use negative 0.537 because I already used the word decreases, which implies a negative change. When we then look at the y-intercept For the y-intercept, we're going to try to describe what happens when x equals 0. So, we're going to say that the average percent of people wearing helmets when biking, which is the variable y, when no children receive reduced fee lunch, which is x equals 0, we find that to be the y-intercept 55.34, again, percent. So when x equals 0, what happens to y? Note that we can interpret in this case because we do see values close to and around 0 for values of x. We see values pretty close to 0 on the x-axis in our scatter plot. If all our values were far above 0, the y-intercept should not be interpreted. Now for r squared, we first need to calculate r squared, which in this case we can do pretty easily because we have the value of r given to us in the example. R is negative 0.849. So all we need to do is square that value and get an r squared value of 0.721. This means when we interpret r squared, we'd say generally that r squared of 72.1%, we'd say that means 72.1% of the variation in y can be explained by y hat, or the linear model. This is the general interpretation. If we apply that specifically to this situation, we would say that if we interpret r squared for percent receiving reduced fee lunch and percent wearing helmets, we would thus say that 72.1% of the variation in people wearing helmets when biking can be explained by the least squares regression line. If you have any further questions, be sure to review the example videos or ask your instructor.